Thanks, Emer, and to the organisers for the opportunity to come and talk to you this morning. I was asked to follow on from Conor to give you an oversight of some of the projections of climate change for river flows and hydrology in Ireland to begin to contextualise what the adaptation challenge is. So in Ireland we have this national climate objective of realising a climate resilient economy, environment and society by 2050 at the latest. Conor Quinlan has identified that part of building climate resilience is around reducing greenhouse gas emissions, that's mitigation, but also in adapting to the impacts of climate change that are happening now and are on the way over the coming decades. And in Ireland, we're not starting from an ideal position. So we have, as we've seen, degradation in water quality. We have ecological and biodiversity crises happening simultaneously, both of which have implications for health and well-being. We've seen the impacts of flooding and vulnerability that exists, and we've seen the challenges of both flood and drought for agriculture over recent years. That leads me to conclude, and indeed we concluded within ICA, Volume 3 looks at impacts and being prepared for future climate, and Chapter 5 within that looks at the water sector. It leads us to conclude within that chapter and volume that water is at the heart of realising a climate resilient Ireland. We need to address water. But we're not starting from an ideal condition. So I wanted to highlight to you in this presentation recent research funded by the EPA through a project called HydroPredict that looks at what the future holds for river flows in Ireland. But before that, I want to talk about the emergence of a climate change signal. This is not just about the future. We're seeing climate change happening around us. We've completed last year, or earlier this year, an attribution study on the floods that happened in Middleton back in October last year in collaboration with Med Éireann and Imperial College London. We all remember the impacts that this flood event had on the community in Middleton, and we're able to show, using both observations and models, that climate change, through increased global temperatures, increased the risk of this kind of flood event by 120%. The biggest impact has been through an increase in heavy rainfall. The two-day rainfall totals that gave rise to flooding in Middleton have increased 13% since pre-industrial times. We expect a warmer atmosphere to hold more moisture, and we're seeing very clearly the evidence of climate change on flood events in Ireland right now. We've also published work showing the emergence of a climate change signal in long-term meteorological records in Ireland. I won't go into the detail. On the right-hand side is a matrix that shows various extreme temperature indices for different seasons. All of those in orange are temperature variables where we see the emergence of a different climate relative to pre-industrial. We see what's happening globally being reflected in Irish temperature records and the emergence of a distinctive climate change signal within those. And it's not just within temperature that we see that happening, we also see it in rainfall. Like I mentioned, we expect warmer atmosphere to hold more moisture and heavy rainfall events to become heavier, and in our data sets we're seeing those, and we can clearly attribute or associate them with an increase in global mean temperature. For every 1 degree rise in temperature, we expect a 7% increase in rainfall intensity, and that more or less is exactly what we're seeing in long-term Irish weather records. To the extent that last autumn, I appeared down in Wexford for an interview with farmers in their fields who couldn't extract their harvest because of extremely wet conditions, damage to their crops. That's the kind of impact from extreme rainfall events in a part of the world, in south of Ireland, where we're seeing the emergence of a climate change signal. Similarly, earlier this year, the challenges because of an extremely wet winter and spring of getting livestock out to farms. So these impacts are already with us. They're not just something in the future. In other EPA-funded work, we're looking at exploring detection and attribution of changes in floods for river catchments across Ireland. These are all of the OPW, their FEMI data set that's used for flood estimation, and you can see those dark blue triangles on the right-hand side are where we see significant increases in the maximum annual flood. And we're able to clearly associate with those on the left, particularly in the Shannon Basin, that these are entirely climate-driven. So it's not because of land use changes, because of climate. And when we go to our long-term records, we see the evidence for global warming being behind these increasing trends. So moving to the future, HydroPredict. This project looked at providing a comprehensive assessment of the impacts of climate change for river catchments, focusing on mean and low flow conditions, to begin to help the kinds of policy making that Conor Quinlan talked about in the previous slide, or in the previous presentation, providing an estimate of the ranges of change, looking across different climate models and different emission scenarios to understand what the impacts may be and how to provide guidance on ranges of change for policymakers. So we looked at river flows, but also looked at drought conditions across the island. As Conor has mentioned, looking at impacts of climate change is not a simple task. It requires us to think about assumptions about future greenhouse gas emissions, what the future world will look like in terms of population and economy and conflict, all of these things, to develop emission scenarios. Those emission scenarios then run global climate models. We use them to force them, and the climate models give us projections of rainfall, temperature, etc. into the future. Then we take those and run hydrological models to look at what river flows might be at the local scale. So it's an involved process. I'm not going to go through all that process, just to show you some of the highlights from what we did. So within HydroPredict, we used the most recent climate model, Ensemble, our family of climate models. They're from the most recent IPCC assessment report, that global climate report. We used 12 of them to make sure that we're characterizing the ranges of changes correctly. And we took 3 different scenarios of emissions into the future. These acronyms get confusing, but SSPs are shared socioeconomic pathways. SSP1 is a sustainable future. We meet the Paris agreements and we maintain global temperatures below 2 degrees Celsius. SSP3 is somewhere in the middle of the road, rivalry, rocky road, and we overshoot that 2-degree target. And SSP5 then is a fossil fuel dependent future. So we took these 12 climate models with these different emission scenarios for sustainable, pessimistic, and middle of the road to have a look at what would happen for Irish catchments in the future. We took 37 catchments across the island, and we looked at applying 2 different hydrological models to each of those catchments. These are widely used in hydrological research in Ireland: a SMART model from UCD, which is a more complex hydrological model, and a simpler model, GR4J. So simple conceptual models. And they work well. I'm not going to go into the detail in the slide. This is for anyone who's interested to see that both of these models perform well during current conditions, so we've kind of confidence in using them for projecting into the future. So what do they show us? And I'm going to show you sustainable and pessimistic futures for, first of all, looking at seasonal mean flows. Can I walk and point on this? I can? Yeah. So here's winter, spring, summer, and autumn. And each one of these is a catchment, one of our 37 catchments from across the country. For winter, here's the 0 line. If you bring it all the way up, you can see for even under the future, sustainable future for GR4J model, we're looking at increases in winter flows across all of our catchments for the 2020s, the 2050s, and 2080s. The further out we go in the future, the bigger the increases in winter. What we find is that spring and autumn tend to be uncertain in terms of the direction of change, but we're moving towards clearer projections of decreasing trends in river flows for the summer period, even under sustainable emission scenarios, SSP 1.6, or the sustainable future. But what's very clear is that even the models that we use for the same inputs give us different outputs. This is for the SMART model for the sustainable future. Again, winter, for each of these catchments, pushing to the right, showing increasing winter mean flows. And in summer, over here, pushing to the left, showing decreases of up to 20% by the end of the century for many catchments across the country. If we have a look at the more fossil fuel intensive future, again, let's just focus on winter and summer. For winter, again, larger increases for each future period, the 2020s, the 2050s, and 2080s into the future. And again, the impact this has for flooding into the future. And then summer, more extreme projections for more fossil fuel intensive futures. Here, looking at reductions in some catchments by the end of the century and summer mean flows by up to 40%. And for the SMART hydrological model, again, looking at seasonal flows for winter and summer, you can see the reductions are less pronounced in summer for the SMART model, but still seeing some catchments showing reductions of between 20 and 30% by the end of the century in summer mean flows. When we look at low flows, we also see some quite substantial changes. So Q95 is the flow that's exceeded 95% of the time. It's the flow that's used for abstraction licensing, issues for water quality, the assimilative capacity of water bodies, etc. And these are the projections from one of the hydrological models for GR4J, or for GR4J for low flows, for the sustainable future, the middle of the road future, and the pessimistic future over here. The middle of the road for GR4J, this is a 20% reduction by the end of the century. Most catchments likely to exceed a 20% reduction in Q95 by the end of the century. And those reductions are even more pronounced when we look at the SMART model for the same metric. So the take-home message here is that all of the models are showing tendency towards large reductions in summer mean flows and in low flows in the future, and in increases in winter flows across all catchments. One of the really important findings from HydroPredict is that when we look at the differences between future emission scenarios, we can see the kinds of impacts we may avoid if we're successful at mitigating greenhouse gas emissions. So if we're successful at meeting that sustainable future target and keeping global temperature to no more than 2 degrees Celsius, down here on the bottom, this is, for example, the blue here is SSP, this is the sustainable future, that's showing modest decreases in low flows if we obtain our more sustainable future versus the larger decreases in low flows if we are not successful at reducing emissions. And similarly, over here for GR4J, you can see the value that is to be had, or the impacts that we avoid if we are successful at reducing greenhouse gas emissions. Okay, so there are river flows. What about droughts? So for droughts, we needed to move to look at a different set of climate model projections that allow us more spatial representation over the country. For that, we looked at meteorological droughts in particular, so looking at rainfall and temperature, evapotranspiration from the Cordex dataset. So these are regionally downscaled climate model projections over Ireland. They come in a gridded format, like in the middle, but we also amalgamated these to look at different regional changes for southern, southeast, western, eastern, and northern. These are European regions. And the Cordex model, we looked at a middle-of-the-road scenario, like our SSP3, and a pessimistic scenario, or late action emissions reduction, across 11 different climate models. And to look at drought, we used a common drought indicator called the Standardized Precipitation or Precipitation Evapotranspiration Index. This is what it looks like if you have a time series. So this is rainfall. As it drops below this standard metric of -1, we say a drought has started, and a drought will continue until it gets back to 0, or average conditions. We can look at different characteristics of drought from this in terms of the duration and number of months from start to finish, or the accumulated deficit or magnitude, the amount of deficit relative to normal for that period of time. And we looked at 2 accumulation periods, shorter droughts using 3-month accumulations, or SPI3, and longer multi-seasonal droughts using SPI6, or SPEI6. And we looked at the frequency, magnitude, and duration of future changes in drought events. And I'll show you the take-home messages here. So for projected changes, this is our reference period representing the current climate. This is RCP 4.5, which is middle of the road future emissions, and this is the more pessimistic future scenario. One thing you'll notice for SPI, so just looking at rainfall alone, there's little difference in terms of the frequency of drought in the future. It's only when we include evapotranspiration with warmer temperatures that we see these large increases in the frequency of drought in the future, and particularly around the east and Midlands and southeast, those darker reds on the bottom left. So the largest changes we see are not from precipitation, but the combination of precipitation deficits and increases in evapotranspiration being the key driver of future drought frequency. If we look at these different regions and look at SPEI, so again, this is looking at evapotranspiration taken away from rainfall, and look at the changes in the drought magnitude for different regions, we can see from present to middle of the road to more pessimistic future, this increase in drought magnitude, particularly in the eastern region, but indeed across all regions, most pronounced in the east. Contrast that with just looking at rainfall only, and we don't see, the same kinds of differences, again, emphasizing the importance of increased temperature in future drought conditions. And over on the right-hand side is duration, again, increased duration when we look at droughts using temperature and rainfall, or SPEI3. The biggest changes are in the shorter droughts, 3-month accumulations, with more modest changes in multi-seasonal droughts, because you have that signal of wetter winters, drier summers. When we look at seasons and look at the spatial distribution of droughts across seasons, this is just for rainfall, SPI. You can see wetter in winter, towards more blues here in terms of drought magnitude. Spring, not so much change happening. In summer, we can see a tendency towards increased drought magnitude in summer, even just looking at precipitation alone. But watch what happens when we look at the combination of precipitation and evapotranspiration. In spring, we see an increase in the magnitude of drought events throughout much of the East and Midlands here in spring. Under even the middle of the road scenario becomes even greater under higher emission scenarios. And then for summer, looking at SPEI, we see a large increase in drought magnitude throughout much of this region of the country and much of the country, particularly the East, Midlands, South, showing an increase in the magnitude of summer droughts by the end of the century under high emission scenarios. So that's a lot to take in. Let me bring it down to 4 take-home messages. First one is that projected changes in seasonal and mean flows do show a wide range of plausible changes, but the overall distribution of change derived from HydroPredict suggests increases in winter flows and decreases in summer flows. We see substantial reductions in low flows, Q95 in particular. They're projected for the 2050s and 2080s across all catchments. And that would prove problematic for a range of sectors, from water quality to agriculture to ecology to water resource management, right across the board. What is critically important is that reducing greenhouse gas emissions results in more modest impacts on summer mean and low flows in particular. Not so much on winter flows, but the evidence from this research shows that the impact of mitigation and reaching our greenhouse gas targets is crucial to avoiding the worst impacts of future droughts and low flows. We find increased drought magnitude, frequency and duration, especially using SPEI, which is including temperature or evapotranspiration losses relative to just looking at rainfall alone, and for the high emissions relative to the more moderate middle-of-the-road emission scenario. This highlights the importance of temperature in exploring future droughts, and we need to be monitoring droughts presently using SPEI, looking at the integration of evapotranspiration, not just rainfall deficits alone, which is a crucial metric to start monitoring and tracking. The greatest risks in terms of future droughts are in the East and Midlands, where SPEI droughts extend from late spring into summer. And the last take-home message is we are already seeing the signal of climate change emerge in observations. We now have evidence to show that it made flooding in Middleton worse. We have evidence to show that we see the impacts of climate change on rainfall and temperature, and indeed following through to floods. So we need to think about how we adapt to these changes. Conor said in his presentation, everybody will need to adapt. And these results will hopefully confirm that too. We need to take adaptation more seriously. And indeed, you're used to adaptation, whether you call it that or not. It's integrated catchment management. Thanks.